Okay, so we have kind of a short one for us today. Let's imagine that we're launching a projectile on an incline, and the incline is at an angle of phi with respect to the horizontal. And then we'll say that the launch velocity of the particle is an angle theta relative to the incline with some speed v naught. And the question is, what angle should this launch velocity be with respect to the incline so that my particle ends up bouncing off of the incline and then retracing the same path coming back down? We'll assume that there's no loss of energy or speed on the bounce, so it's perfectly elastic. Okay, now something we're going to be using here is a result that's been proven previously, which is that the slope of this line, the slope of this secant that connects our launch point to the point of collision, is actually the average of the slopes of the two tangents at those 2 points. So this will be half the sum of the slopes of these two velocities, the initial velocity and the final velocity. So clearly here, if I call this, say, theta naught, and I want to be a little careful here because all of these slopes are going to be measured relative to the horizontal. So tan phi is basically the slope of this line relative to the horizontal. I'll call theta naught this whole initial angle all the way down to the horizontal theta naught. And then over here, where we have our impact, there'll be some tangent. The velocity at this point will be in this direction, at least immediately before it collides with the ramp. And maybe I'll call the angle that this makes with the horizontal theta final or something like that. Now, the general result we proved earlier was that the slope of the secant is the average of the slopes of the tangents. Notice that this slope is negative, but I kind of want to work with positive angles here. So I'm going to say that theta f is a positive number. That does mean I need to put a minus sign in here when I'm calculating the slope of that line. So that'll be the tangent of this final angle. Okay, now we just need to do a little bit of some basic geometry and a little trig. So first off, like I mentioned before, we'll say that theta naught, this initial launch angle, is just my slope angle plus the angle relative to the slope. Okay, that's not so bad. And then we need to work out what theta f is in terms of these things. And hopefully it's not too hard to see that if we drop a little perpendicular here, theta f and phi, which is this angle as well, are complementary angles. So theta f is just going to be 90 degrees minus phi. Okay, so let's sub those in here. I'll move the 2 over as well. Okay, so there's our sort of semi-simplified result. And of course, the goal here is to figure out what theta has to be. We might also want to mention physically that this angle that the projectile collides with the ramp at has to be 90 degrees. This theta f velocity vector has to be orthogonal to the ramp. If it wasn't, then we wouldn't actually retrace our path. For example, if it came in a little too shallow, it would actually bounce forward a little bit, possibly, and not retrace this path, or maybe bounce back at some slightly higher angle. And if it was coming in too steep, then it would underbounce on its way back down. So we really do need this red line to be orthogonal to the ramp. Still, we can go ahead and try to simplify this a little bit and solve for theta in terms of phi. Okay, so how can we do that? Let's use our tangent sum identity on this term, and we'll use our cotangent, or really co-function identity on this tan 90 minus theta. Okay, now let's go ahead and, whoops. Sorry, that should be a phi. Okay, now let's go ahead and maybe cross multiply this denominator to both sides and see what we can clean up. Okay, so double checking everything here. Multiplying this over on this side, I'll get a 2 tan phi and then minus 2 tan squared phi tan theta. And then I'll be left with my sum here with no denominator. Multiplying this over, I'll have that minus 1 times cotan phi here. And then this minus minus becomes a plus. The tan phi and cotan phi cancel, and I'm left with just a tan theta. A lot of these terms can now be simplified. For example, this tan phi and one of those tan phis can cancel. This tan theta and this tan theta can double up and give me 2 tan theta. So then what I'm going to do is I'm going to add this over to the other side. I'll factor out everything that's not attached to the tan theta, or that is attached to the tan theta, and isolate tan theta. So what will I have? I'll have tan phi plus cotan phi. Those actually will simplify in a sec. And then after factoring things out, there'll be a 2, and I'll have tan squared plus 1. Okay, now at this point, after we've sort of factored out that 2, let's go ahead and factor a cotangent out of the numerator. And what we'll be left with is a 1 from this term and then a tangent squared from this term. But of course, that's the same as the denominator. So our final result is that this tangent of theta is actually just half of cotangent phi. All right, so that's the angle we should launch this so that it actually will rebound. We could go ahead and pick some particular numbers, for example. If this was, for instance, launched at a 45-degree angle, then we know that this cotangent will just give me a 1, in which case my theta should be the arctan of a half, or if you want, the arccotan of 2, either way. Okay, so there it is. We've got the relationship we want. The launch angle that gives us a retraced path is the arctangent of half the cotangent of phi.